Hi, I'm Mr. B, and this is the Learning Zone. After watching this lesson, you will understand why and how to report measurements in the laboratory using significant figures. You know, significant figures are based on measurements where in a laboratory measurements may be taken using a variety of different instruments. For example, mass measurements may be taken by use of an electronic balance. Rough volume measurements may be taken by use of a beaker, while finer volume measurements may be taken by use of a graduated cylinder. And of course, the use of a serological pipette will yield the greatest accuracy. Let's use a volume measurement as an example. Say you're in a chem lab and you need 15 milliliters of water. You could use a graduated cylinder marked in 1 milliliter increments to accomplish this task. With the graduated cylinder, you could easily obtain a volume between 14 and 16 milliliters. This measurement contains two significant figures, where the 1 in the tens place is a certain digit. However, the 5 in the ones place is an estimated digit. Any measurement will contain certain digits and one uncertain digit, where the uncertain digit will be the last digit in the measurement. You know, regardless of the type of measurement being taken in the laboratory, if the instrument being used is not both accurate and precise, then the data taken by using that instrument is essentially useless. The accuracy of a measurement system is the closeness of the measurements to the actual or true values. The precision of a measurement system is related to the reproducibility and repeatability of the measurements, and is the degree to which the measurements under unchanged conditions show the same results. Consider this target system, where on the left side we have examples of low accuracy and low precision. And on the right side we have an example of low accuracy and high precision. Clearly, these are examples that will generate inaccurate results. On the bottom on the left side, we have a system with high accuracy and low precision. In other words, the data is kind of all over the place. Where on the right side, we have a system that shows both high accuracy and high precision. Consider this example. Let's measure a 5-gram mass demonstrating both high accuracy and high precision. In the first case, the measurement yields a value of 5.0002 grams. And in the second case, the balance shows a mass measurement of 4.9998 grams. Clearly, this is an example of both high accuracy and high precision. On the other hand, a system showing low accuracy and high precision may yield values as follows, where the 5-gram mass is measured to be 4.0012 grams in the first case and 3.9598 grams in the second case. Clearly, in this particular case, the balance needs to undergo a process called calibration. The rules for determining significant figures are fairly straightforward. For example, number 1, all non-zero numbers, those are numbers from 1 to 9, are always considered to be significant digits. Number 2, all zeros written in front of non-zero numbers are never significant. For example, 0.0015 grams contains 3 leading zeros. These zeros are not considered to be significant digits. Number 3, all zeros written between non-zero numbers are always significant. For example, 1001 grams contains 2 embedded zeros. Embedded zeros are always considered to be significant figures. Number 4, all zeros which are simultaneously to the right of a decimal point and at the end of a number or measurement are always significant. For example, 225.00 grams contains 2 trailing zeros. If a decimal point is included, trailing zeros are always considered to be significant digits. And number 5, all zeros written at the end of a measurement are never significant unless followed by a decimal point. For example, 700 grams contains 1 sig fig because there is no decimal point after the zero. However, by placing a decimal point after the last zero, the measurement now becomes 700 point grams, which indicates that the measurement contains 3 significant figures. Now let's apply the rules for determining significant digits to some actual examples. Consider the following. How many significant figures are present in the following numbers? Where the first number is 48,923. This measurement contains 5 significant figures because all the digits are non-zero digits. 3.967 contains 4 significant digits for the same reasoning. 900.06 contains 5 significant digits because this measurement contains embedded zeros, and embedded zeros are always considered to be significant. And finally, 5,000 point contains 4 significant figures because the trailing zeros are followed by a decimal point. Suppose you are to report a measurement using scientific notation. This is how it's done. 0.0004 may be rewritten in scientific notation as 4 times 10 to the minus 4. This measurement contains 1 significant digit. 7,001 may be rewritten as 7.001 times 10 to the 3. This measurement contains 4 significant figures. 3 million may be rewritten as 3 times 10 to the 6, but because there is no decimal point, the trailing zeros are not significant. This measurement contains 1 significant figure. And finally, 10.0 may be rewritten as 1.00 times 10 to the 1. This measurement contains 3 significant figures. This concludes my lesson on why significant figures are important when reporting data in a laboratory and how to report data using significant figures. Join me for my next lesson where I'll explain how to use significant figures in calculations. Hopefully this video has been helpful. Thanks for watching.